95% of the territory in Saudi Arabia is occupied by barren desert, creating a landscape where rainfall is almost entirely non-existent. Why would a nation surrounded by sand and salt water attempt to build a massive steel delivery system across such a hostile environment? At first glance, the task of hydrating a country with such geography seems impossible, but in reality, the survival of the entire population depends on a complex engineering network that connects the Red Sea to the heart of the mainland. The process is only gaining momentum. Every 24 hours, billions of liters of raw seawater are drawn into massive desalination complexes with a steady, powerful suction. This liquid is then forced through a pipeline network that stretches across several thousand kilometers of shifting dunes. One can notice how the equipment gradually manages the immense pressure required to move these volumes. Bringing water from the coast to the interior is a significant physical challenge, but the true technical achievement lies in the conversion of salt water into a resource suitable for human consumption, large-scale agriculture, and heavy industry. It only looks obvious to move water from one point to another, but in reality, maintaining the chemical purity and flow within these steel arteries requires constant monitoring and high-grade materials. The process does not end at this stage. Automated systems and massive pumping stations drive this invisible river through the desert heat. One can see how the camera glides along the endless rows of welded steel pipes, which must withstand the corrosive effects of the salt and the extreme thermal expansion of the sun. Therefore, the construction and operation of such a system represent a pinnacle of modern industrial infrastructure. From here, the transformation of the desert landscape moves to the next phase of development. 37 million people reside within the borders of Saudi Arabia, with nearly the entire population adhering to the tenets of Islam. Why is the demographic distribution of this nation so heavily skewed toward its maritime borders? A dense concentration of inhabitants occupies the regions directly adjacent to the Red Sea coast and the Persian Gulf, while the vast interior of the kingdom remains a silent and almost entirely uninhabited desert. Saudi Arabia possesses the single resource the global economy desires most, which is oil. 40 trillion liters of crude oil lie beneath the arid soil, yet nature has not provided a balanced environment for human survival. Despite this subterranean wealth, the government is forced to spend billions of dollars to generate every single drop of fresh water required for its citizens. It is visible how the environment resists life, with average annual rainfall measurements falling below 100 millimeters and summer temperatures regularly climbing above 45 degrees Celsius. To survive under these harsh atmospheric conditions, the state engineered and constructed a nationwide water pipeline system. At first glance, the infrastructure appears standard, but in reality, it is a feat of extreme engineering. The network utilizes high-strength carbon steel pipes with technical specifications nearly identical to those found in the high-pressure oil and gas industry. But this is just the beginning. The financial investment required for this hydraulic lifeline is immense. Construction costs for the network average approximately $3 million for every single kilometer of pipeline installed. This figure does not include the essential booster pumping stations or the advanced desalination plants, each of which requires an investment of tens of millions of dollars to remain operational. But where exactly does this massive pipeline network source its liquid cargo? They turn to the nearly inexhaustible volume of the surrounding seawater. However, raw seawater contains a salt concentration of approximately 3.5%, a level far too high for human consumption or agricultural irrigation. One can notice how the equipment must work ceaselessly to remove these minerals. This necessity led to the development of sophisticated desalination technology, which now provides the kingdom with a nearly unlimited supply of usable water. The pipeline carries the processed water directly from massive desalination facilities situated along the Red Sea. The process is only gaining momentum as these industrial complexes operate 24 hours a day. Each individual plant is capable of converting 7 million liters of seawater into potable drinking water every single day, though the process consumes a massive amount of energy to maintain the necessary pressure and heat. Everything only gets more complicated as the water is pushed through the steel veins of the desert. The liquid passes through the high-strength pipes toward the cities, completing its transition from the sea to the tap. 1,800 millimeters is the diameter of the high-strength carbon steel pipes that form the backbone of a transnational water pipeline. Why is such a specific metallurgical composition chosen for this infrastructure? The material mirrors the steel utilized in high-pressure oil and gas conduits to ensure the system can withstand the relentless force of pumping pressure and the physical stresses of underground burial. But this is just the beginning. The steel must also endure the extreme thermal cycles of desert environments, where temperatures fluctuate violently between day and night. At first glance, the preparation of the raw material seems simple, but in reality, it requires mathematical precision. Industrial shears cut rectangular steel plates into pre-calculated dimensions that will eventually form the circular structure. One can notice how the heavy plates, featuring a wall thickness of nearly 25 millimeters, are fed into a multi-axis rolling machine. The equipment gradually applies pressure through a series of rollers that bend the metal step by step. The process is only gaining momentum as the two edges of the plate are forced together to create a pipe blank, establishing the foundation for the upcoming longitudinal welding phase. Because the welding process generates intense localized heat, the pipe is immediately passed through a straight-flow water cooling line. It is visible how the liquid lowers the temperature of the weld seam to stabilize the crystalline structure of the steel. Everything only gets more complicated as the pipe moves to the finishing station. Automated grinders move along all edges and corners of the steel cylinder to remove burrs and irregularities. This ensures the geometric accuracy of the unit before any further welding is attempted. The camera glides along the ends of the pipe, where beveled edge welds are meticulously finished to create optimal contact surfaces. These angled profiles are critical for ensuring perfect joint connections during the final assembly. 12 meters is the standard length of each individual pipe section produced in the facility. This specific measurement is chosen because it effectively reduces the total number of welds required for the project, while remaining within the limits of practical transportation. Such a design allows the segments to be joined quickly in the field, maintaining pressure-tight seals that remain structurally stable over decades of service. Transition to the next level. The completed steel pipes are transferred to an outdoor storage yard with the hiss of heavy hydraulics. Here, the sections are stacked in organized batches and clearly marked with tracking codes for logistics management. The equipment gradually lifts the pipes onto specialized transport vehicles using heavy-duty forklifts or overhead cranes. Each section is securely fastened with reinforced straps to prevent any physical deformation or shifting during the long transit. Hundreds of kilometers of desert and rugged terrain separate the factory from the active construction site. The pipe sections are hauled by heavy convoys directly to the cross-country pipeline route. There, the final integration begins as the segments are welded together into a continuous line. The molten stream of the final field weld goes further along the production chain. 40 meters of width. This is the standard span for a construction corridor prepared in advance to allow for a continuous pipeline installation. Large staging yards located along the desert route serve as the primary logistics hubs where the process originates. Why is such meticulous grouping of steel pipe sections necessary at these desert outposts? The environment is unforgiving, and a single logistical error can halt the entire production chain. Sections are categorized by their specific diameter, length, and their predetermined sequence in the installation schedule to ensure a seamless flow of material. Engineering teams carry out final visual inspections on every segment. They verify pipe straightness, the integrity of the external coating, and the clarity of identification markings with high precision. Proper organization at these staging areas is mandatory to maintain a continuous workflow and minimize delays in harsh desert conditions. At first glance, the desert seems like an open canvas, but in reality, every meter of the route is dictated by complex terrain data. One can notice survey teams establishing the exact alignment across the dunes using high-precision GPS systems and total stations. The process is only gaining momentum. Stakes and visible paint mark the path directly on the ground to guide the heavy machinery. This ensures the pipeline follows the most stable and efficient route possible, avoiding areas with weak soils or shifting sands prone to erosion. For systems stretching hundreds of kilometers, this accurate routing is the foundation of long-term structural integrity. The construction site must be cleared and leveled before any trenching can occur. Temporary access roads are opened parallel to the route to accommodate an endless stream of trucks, excavators, and welding rigs. In the desert, site preparation also involves active dust control and sand stabilization measures to maintain visibility. One can notice the water trucks dampening the sand as the equipment gradually moves into position. Everything only gets more complicated. Large tracked excavators begin digging the trench along the marked alignment with mechanical rhythm. The trench is carved to a precise width and depth to provide sufficient space for pipe placement and subsequent backfilling. Excavated soil is sorted on site, where suitable material is retained and unsuitable rock is removed. Maintaining a consistent depth is essential to prevent pipe deformation once the weight of the desert sand is reapplied. But what happens when the pipeline encounters solid rock in rugged mountain terrain? Mechanical excavation becomes impossible against the bedrock. Engineers place controlled explosive charges and detonate them in a timed sequence to fracture the stone along the planned path. The resulting blasted trench creates enough depth to seat the pipeline securely even in extreme landscapes. Transition to the next level. After excavation, the pipe is never placed directly onto the raw trench floor. A layer of selected material, typically fine sand or screened soil, is spread evenly along the bottom to create a soft bedding. This layer distributes loads uniformly and reduces stress concentrations on the steel skin of the pipe. The bedding is leveled and lightly compacted to achieve the required elevation for the heavy sections. The construction corridor allows for an average installation pace of approximately 1.5 kilometers per day. Pipe sections measuring 18 meters in length are selected to reduce the total number of field welds required. This length imposes very high demands on lifting and transportation equipment due to the immense weight and center of gravity. At the welding site, a hydraulic internal line-up clamp is positioned inside the joint. It is visible how the 360-degree gripping shoes expand to hold the two sections perfectly concentric. This alignment is maintained throughout the critical root pass of the weld. An automated welding operation, supported by a workforce of roughly 80 personnel, can complete up to 150 welds per day. Every single joint undergoes automated ultrasonic inspection to identify any internal defects that could lead to a leak. It only looks obvious to move to the next stage, but in reality, the joint must be perfectly sealed first. Field joint coating crews perform abrasive blasting to strip the metal to a clean surface. They apply a multi-component liquid epoxy coating to form a durable, fully sealed protective layer. The assembled pipes are then lowered into the trench using specialized side crane tractors. Multiple side booms operate in a synchronized sequence, lifting the heavy pipe string with padded slings to protect the fresh coating. It is visible how the pipe string is raised evenly and held suspended as the machines move slowly. Precise coordination between operators prevents the steel from twisting or striking the trench walls. When aligned, the pipe is lowered gradually, centimeter by centimeter, until it rests on the center of the bedding. Surveyors monitor the elevation and natural curvature throughout the descent to ensure no residual stresses are introduced. This method allows for fast and highly accurate placement across the flat desert floor. The trench is finally backfilled in multiple layers once the pipe is positioned. The initial layer consists of fine material to protect the coating, followed by the original excavated soil. Each layer is mechanically compacted to achieve the required density and minimize future settlement. In desert conditions, this compaction is critical for the longevity of the infrastructure. The material is buried and protected, allowing the desert surface to return to its original state. 1,000 meters offshore is the point where the life cycle of the facility begins as seawater is drawn directly from the open ocean into the system. Why is such a distant intake point necessary for the desalination plant? Drawing water far from the coast ensures a steady and uninterrupted supply of raw water that remains free from the heavy sediment found near the shoreline. This establishes the vital foundation for the entire inland filtration process. But this is just the beginning. Installation crews first position large intake lines across the surface of the water using heavy lift cranes. These massive components are maneuvered with millimeter precision from the decks of specialized barges or coastal platforms. The equipment gradually aligns each individual section of the pipe before lowering it into the depths. It only looks obvious to submerge the lines, but in reality, the underwater environment requires the machinery to fight against currents to maintain the correct trajectory. As the pipeline extends toward the shoreline, individual segments are connected sequentially to form a continuous conduit. Each joint must be sealed to withstand a constant hydraulic load for decades. One can notice how the connectors are tightened until the structure becomes a single rigid artery for the ocean water. The process is only gaining momentum. Precision alignment is critical at this stage because even minor deviations of a few inches can compromise the long-term flow efficiency and structural integrity of the line. Therefore, every section undergoes a rigorous verification of its coordinates against the engineering plan. The camera glides along the length of the submerged pipe, where the metal lays in a perfectly straight line along the seabed. It gets more complex further on. Once the primary assembly is complete, the intake line is reinforced with heavy structural support frames. These units are securely anchored to the seafloor to prevent any shifting caused by underwater turbulence or storms. It is visible how the anchors grip the terrain to stabilize the massive weight of the conduits. The water now begins its movement toward the inland pumps, transitioning into a calm stage of preparation. 15 million liters per day. This is the immense volume of seawater pulled into the desalination system through heavy-duty intake pipelines. The process originates several hundred meters away from the shoreline, where the intake mouths reside on the seabed. Why is such a vast distance from the coast necessary for the initial intake? Drawing water from the deeper offshore zones ensures a more consistent temperature and lower initial turbidity. This positioning allows the heavy steel barriers and primary intake filters to effectively block large floating debris and marine organisms before they enter the internal conduits. 150 millimeters of diameter is the standard for the heavy-duty piping, but a larger 63-centimeter pipe can move over 10,000 liters of water every single minute. Powerful centrifugal pumps at the intake station exert constant force to push the raw seawater toward the processing plant facilities. It gets more complex further on. One can notice how the water moves with significant velocity, yet it carries unwanted biological matter like jellyfish, small crabs, and various fish species. To prevent these organisms from clogging the sensitive internal machinery, a massive mechanical screen is positioned to block any object larger than 4.5 millimeters in diameter. Finer secondary screens follow this stage to capture any remaining large-scale particles that bypass the first barrier. At first glance, the water may seem relatively clear after these physical barriers, but in reality it remains saturated with suspended sediment and fine silt. The equipment gradually directs the flow into specialized filtration tanks, where the water descends through thick, multi-layered beds of sand. Gravity pulls the liquid downward, while the sand grains, packed tightly together, act as a microscopic sieve that traps suspended solids within the narrow gaps. The sand particles move in a continuous downward motion that is opposite to the upward or lateral flow of the water. Dirty particles cling to the rough surfaces of the sand grains through physical adhesion, leaving the water significantly clearer as it exits the tank base. But this is just the beginning. Even though the water looks transparent to the naked eye, it still contains millions of microscopic particles that are roughly 1/10 the thickness of a human hair. The process is only gaining momentum. Large mechanical paddles rotate ceaselessly to stir the liquid as the plant introduces two specific chemical agents. Sodium hypochlorite acts as a primary disinfectant to neutralize biological contaminants, while ferric chloride serves as a technical coagulant. This coagulant forces the microscopic sand and waste particles to bond together, forming larger clusters known as flocks. One can notice how these heavier flocks gradually lose buoyancy and settle at the bottom of the sedimentation tank. Most visible impurities have been eliminated at this stage, yet the liquid is still not refined enough for the high-pressure membranes. Transition to the next level. The water enters the cartridge filtration system, which functions as the final physical line of defense before the primary desalination phase. Inside these heavy-duty housings are multiple cartridges constructed from layers of tightly compressed synthetic fibers. Pore sizes within these fiber cartridges are restricted to between 1 and 5 microns. As the pressurized seawater flows from the outer edge toward the hollow center of each unit, microscopic debris is trapped within the fiber mesh. Clean water passes through the cartridge walls and continues into the high-pressure manifold. Once a filter element becomes saturated with trapped particles, engineers must manually remove and replace the cartridge to maintain the peak hydraulic efficiency of the plant. Seawater now moves toward the most critical technical stage, where the salt is physically separated from the water molecules. Salt is notoriously difficult to isolate because the individual ions are locked to the water molecules through intense electrostatic attraction. To overcome this molecular bond, the system must generate a force that exceeds the natural osmotic pressure of the brine. This is the stage of reverse osmosis, where the physical transformation occurs under extreme mechanical stress. High-powered centrifugal pumps are utilized to generate the necessary hydraulic energy. Each individual component of this pumping assembly manages a specific pressure increment, ensuring the water reaches the required energy level in successive phases. By the time the liquid exits the final compression stage, the internal pressure reaches 60 bar. This is 60 times the pressure of the atmosphere at sea level, providing enough mechanical energy to force water molecules through the ultrafine membranes while leaving salt ions behind. After the initial round of reverse osmosis, the water is nearly devoid of salt, but it still retains trace ions and microminerals. To achieve the strict purity levels required for human consumption, the stream is sent through a second stage of reverse osmosis. These secondary membranes operate under a lower pressure, but are designed with a much higher efficiency for salt ion removal. One can notice how the electrical conductivity of the water drops to extremely low levels, indicating that the remaining ions have been successfully stripped away. The result is a stream of ultra-pure water that has reached its maximum level of cleanliness. However, this water is not yet ready for the public grid because it lacks the necessary chemical balance for safety and taste. After passing the membranes, the water is clean enough for agricultural irrigation, but the pH level must be stabilized. The plant operators introduce a precise amount of acid or a balancing alkaline solution to bring the pH back into a neutral, safe range for human biology. Reverse osmosis water is so pure that it lacks the essential minerals found in natural spring sources. To improve the overall quality and the sensory experience for the consumer, the facility adds controlled amounts of calcium and magnesium. This remineralization process restores the mineral profile of the liquid, increases its alkalinity, and provides the natural flavor profile expected of drinking water. It is visible how the water transforms from a purely industrial product into a healthy resource for the population. Modern pipeline networks then distribute this desalinated water across the arid regions of Saudi Arabia to serve residential centers. This infrastructure represents a massive investment in survival, as the cost of production is remarkably high. 1 cubic meter of water costs approximately $5 to produce in this environment. In contrast, the same volume of water in the United States may cost only a few tens of cents to process and deliver. Thus, the steel and concrete of the desalination plant fulfill their role in providing the most vital resource for life.